now move on. Okay. So a brief guide to the geology of the moon. What's my interest in the geology of the moon and why am I talking to you about it? Well, my background is igneous petrology, and I spent quite a lot of my career looking at alkali basalts associated with subduction from Antarctica. And more recently, I've been looking extensively at continental flood basalts. However, about 6 years ago, Aberdeen University set up a department of planetary science. Planetary science department largely staffed or entirely staffed by engineers and physicists, and they wanted some geological input. So we run an MSc course, planetary sciences, and myself and my colleague Alex Brazier, we deliver modules about planetary geology. So that's how I've come to be working on planetary geology. But that's not the whole tale. Because, and looking around this room, I'm sure most of you remember something that happened or remembered what you were doing on the 20th of July, 1969. I suspect you were watching telly. Probably a 405 line black and white job. It might even be that some of you had to hold the aerial, get a decent signal, and when it started rolling around, you bang the top to stop it rolling. I remember that very, very well indeed. So in 1969, the first moon landing was something ingrained in my memory. I was a 9-year-old boy. I was very interested in the Apollo missions. 9-year-old boys know a lot about Apollo missions. Okay? Fast forward 50 years, I end up being faced with a planetary science department and then saying to me, hey, what can you tell us about the geology of the moon? And I said, well, I can always research into it, which is what I did. Then along came COVID, and I didn't have anything else to do with my time other than research the geology of the moon. So that's what I did. Okay. Some vital statistics about the moon. Diameter 3,476 kilometers, density, bulk density, not dissimilar to Earth. Atmosphere, well, none. That's important because anything flying through space that's heading for the moon doesn't burn up in the moon's atmosphere, it hits the moon. So the moon has a massive impact history, unlike Earth, where things attempting to get to Earth's surface tend to burn up in the atmosphere. It's a silicate planet, it's a silicate, more correctly, satellite, and its gravity is about a sixth of that of Earth. And now my pointer's stopped working, never mind. I think, in fact, PowerPoint stopped working.
It's okay. Right, it should work. Oh, your thing's spinning.
Oh, right, okay, fine, yeah. This is just a diagram to put everything in a kind of proper perspective. So you'll see the Earth and Moon at the relatively correct scale and the correct distances. The rule at the bottom is courtesy of Wikipedia. But one of the things I want to point out here is that at the perigee and the apogee, there's a difference of the distance from the Moon to the Earth of around about 50,200 kilometers. Now, when the Moon is closest to the Earth, and it's a full moon, that's when we get a supermoon, and the next one of those next week, 5th of November, okay? So there we go. The moon has an irregular orbit around the Earth. So, as I say, a Mars-sized body is thought to have impacted into the molten Earth, a thing called Theia. This is supposed to have happened at the very initiation of accretion of the solar system 4.5 billion years ago. The debris from the impactor and from the proto-Earth is what formed our moon. So when the moon formed, it was like a lot of the other silicate bodies in the solar system. It was a magma ocean, a completely molten body. Now, if we look at this from a very general cartoon perspective, if to start with we had a uniform reservoir of material, a magma ocean like that, then what happens is in the first few tens of millions of years, if it's going to happen at all, you start to form a core. And of course, on Earth, what we have is a solid inner core, liquid outer core, and the differential rotation of those two gives us our magnetic field, Earth's magnetic field. The moon doesn't have much of a magnetic field, so it probably doesn't have a solid inner outer core, but it's likely to have a core made of iron and nickel. And then, of course, through geological time, each of the terrestrial planetary bodies and their satellites, if they're silicates, will differentiate into a layered system, and that differentiation takes place largely by magmatism. And on Earth, this is quite a profound layering because we have active plate tectonics, which of course doesn't exist on the Moon. Here's a picture of the Moon that dates back, it's an ambrotype from the mid-Victorian era, and it was what the first astronomers observed about the Moon. And what they observed was two terrains. One, the shiny terrain down in the southeast there, which is also quite elevated and pockmarked, and the darker terrain, much flatter, darker in colour, less reflective. And of course, in those Victorian days, they jumped to the conclusion straight away that the Moon was just like a little Earth, and it had continents and oceans. So they called the dark flat patches mare, or maria, and we still use that term today. So Apollo 11 landed in the Sea of Tranquility. What we now know about these seas is they're entirely made of basalt, which makes them very interesting. Okay, fast forward to the most modern renditions. This is from a web facility called LROC QuickMap. LROC is the Lunar Reconnaissance and Orbiting Camera. It's a NASA invention. This is an interactive website, and you can play with the moon globe and put layers on it and all sorts of things. If there's time, I'll show you at the end. But it's just to illustrate that on the near side of the Moon, we can still see, now in much greater detail, we have these large flattish areas, the lunar maria, and a much more intensely impacted lunar highlands. Okay? So we only ever see the near side of the Moon. We don't see the far side from Earth. Why? And this is a process known as tidal locking. And what it means is that the Moon does a single rotation around the Earth at the same rate as it rotates around its own axis. So on the left-hand side, you can see the Moon goes round and round and round, but the near side of the Moon always faces Earth. If the Moon didn't rotate at the same rate, we'd have a situation on the right, and we'd see different aspects of the Moon during its orbit of the Earth. Now, this tidal locking mechanism is quite important. It has some underlying significance for theories of the evolution of the Moon. It's unusual because there's only the Earth-Moon couplet that shows this, and the only other perfect tidal locking in the solar system is Pluto and one of its moons, Charon. So that's an important point, tidal locking. Right, so the near side, here it is again. We've known about that for a very, very long time. There's plenty of early astronomical observations of the near side of the Moon, but the far side was first observed by the Lunar 3 spacecraft in 1959, and the first human eyes didn't see it until Apollo 8 in 1968. So the far side of the Moon was a bit of an enigma. As you can see, the near side and far side are quite different. Near side dominated by the dark patches of the lunar maria, the far side dominated by what's known as the highlands crust. And this difference between the near and far sides is known as the lunar dichotomy. And the lunar dichotomy is something that will pop up a few times during this talk. So we have this lunar dichotomy, which is a morphological difference in the surface features of each side of the Moon. This is the Moon as a topographical map. It's an orthographic projection, so projected onto a cylinder and then flattened out. And it's just to illustrate the point that if you take the Challenger Deep on Earth as the deepest point and Everest as the highest point, then the topographical variation on the Moon is around about half that we see in total on the Earth. But you will see, again, the dichotomy where all the lunar maria and the lowland areas are on the near side of the Moon, and the highland areas are concentrated on the far side. Why do we know so much about the Moon? Why on earth did the Americans decide to go there? Well, this in itself is a very interesting story. So the geopolitics and economics of the time drove this. So Kennedy said in 1961 that by the end of the decade, that was by the end of the 60s, he wanted to return a man from the Moon safely And this amazingly was achieved. Why? Well, the geopolitics at the time, in 1962, when he made that promise, it was before the CIA-sponsored attempted overthrow of Castro. It was before the Cuban Missile Crisis. So we're at the height of the Cold War, and rocketry and satellite imaging and satellite surveillance was really important strategically. So there was a massive political will for development of technology. And to a certain extent, that was glossed over by saying this is scientific exploration, this is geological exploration of the moon. So in the 60s as well, at that time, global economies were booming. So we had this unique situation of a political will right from the top and an endless pot of money. And that's what gave rise to the Apollo missions. We also have to have the right people. This gentleman is Wernher von Braun. Wernher von Braun designed the Saturn V rocket. He's a German. He was director of NASA at the time of the Apollo landings, personally congratulated by President Nixon for his achievements. And there you see him dressed in a rather natty 1960s suit with one of those ties that was designed to strangle you. He didn't always dress like that. 25 years earlier, you would have seen him in a black uniform because he was a Sturmbannführer in the Allgemeine Schutzstaffel. In other words, he was a Nazi officer. At the end of the Second World War, von Braun and all his rocketry team disappeared off the face of the earth and reappeared in the United States. This was the forerunner of the CIA running something called Operation Paperclip, and they wanted the technologists involved in rocketry in the US. And that's where Wernher von Braun came from. You don't find that mentioned in much detail on NASA's website, oddly enough. Okay. Wernher von Braun designed these things. That's the V2. They dropped 1,402 of them on the UK, largely built by slave labor from concentration camps. Let's gloss over that. Quiz time. How many astronauts were trained geologists? All of them. All right, this I got from NASA's archive. This is the lecture series that the astronauts, all of them, had to go through. I'm particularly taken by the stuff on the right at the bottom, 7 igneous rocks, origin, composition of primary magmas, phase relationships. See Bruce Mayer starting to go weak at the knees with phase relationships, differentiation, rate of cooling, intrusion. Fantastic, lots of igneous petrology. Here's the best bit though. Time in hours, 58 hours in series 1, and that's series 1 of 6. 360 hours of taught geology before you could even get into NASA. Quite remarkable. And just to prove it, middle of the field of view there is Neil Armstrong, 1964, in the Grand Canyon, doing some stratigraphy. There we have it. The other really important perspective we have to have is what we knew about the geology of planet Earth in 1960s. Well, we can put quite an interesting perspective on that by looking at this paper. This paper was published on September the 7th, 1963. It's quite famous. Fred Vine and Drum Matthews. And what's it about? It is the first systematic description of symmetrical magnetic seafloor anomalies along the Reykjanes Ridge. Okay? So this is the foundation paper that led to the modern theory of seafloor spreading. This was the paper that actually said seafloor spreading genuinely is a thing, and we can see how fast it happens. So we now have a driving mechanism for plate tectonics. 1963, that's just 6 years before the first return of moon rocks. Now, when I was an undergraduate student at Birmingham in the late 1970s, plate tectonics was taught as a module as part of a degree. And the vast majority of the staff hadn't embraced plate tectonics at all, right into the 70s. Okay? It was taught as a kind of special extra thing that's nice and new. So that's something else worth thinking about. There's a well-known saying that we also know more about the surface detail of the moon than we do about the oceans. That was said in the 1960s. It's still true to this day. And it's perhaps no surprise that the first systematic ocean drilling of the ocean crust took place with Glomar Challenger in the summer of 1969. The fact is that the first rocks from the moon got to laboratories at NASA before the first basalts that were drilled from the ocean floor. Okay? I wonder which one caused the other. Right, back to the moon. I said we know more about the surface of the moon than we do about our own oceans. This is absolutely true. There's the moon. We can map all sorts of things using modern computer technology, so we can put on the mare boundaries very accurately. That's the flood basalts that form the near side of the moon. On top of that, we can make measurements of elemental concentrations on the lunar surface. This is a map of how much iron is in lunar rocks. It works because there's no atmosphere, there's no vegetation, no water. We're looking at bare rock. Iron abundance is calibrated from about 0 to 25 weight%. Incidentally, if you find a basalt on Earth with 25 weight% iron in it, you write a paper on it straight away. But it's quite common on the moon. Okay? So we know a lot about the composition of the lunar surface. If we look at it in terms of titanium concentration, we've got plenty of information on that as well. You'll also see that the scale on there, titanium concentration is up to 10%. Some basalts on the moon have 15% titanium in them. That's about 10% more than the maximum that you ever see on Earth. Quite unusual. Thorium. Yeah, thorium has a long-lived radioisotope, 232 thorium, easily detectable from space, from satellites. That's a map of thorium on the moon, up to 10 parts per million. This is a particularly interesting terrain, and it's called the Procellarum creep terrain. CREEP is an acronym for potassium, rare earth elements, and phosphorus. And the Procellarum creep terrain, we also now know that it's got a lot of thorium in it as well, is a geochemical anomaly that's obviously near surface on the near side of the moon that gets the name of a particular terrain to it. Okay, titanium abundances are at such a high resolution, you can even see the effect of a post-Mare collision. This is Copernicus crater. It's been cratered, it's burrowed through the lunar mare into the underlying crust, and it's distributed that material as an ejector blanket, and you can see the radial ejector lines. So phenomenal resolution of these things. Near side, titanium abundance. Far side, titanium abundance, pretty well zero. So what do we have? We have a lunar dichotomy in relationship to composition as well as to morphology. All right. So a manned mission sample return, classic picture of an astronaut standing next to a big rock with his lunar rover. This is the grainy TV image I was talking about. This is Neil Armstrong. One small step for a man. There's lots of conspiracy theories saying that he didn't quite get it right, but we'll leave those for just for now. So that was Apollo 11, 8:15 on the 20th of July, Sunday the 20th of July, the first man landing on the moon. A few weeks later, the glossy magazines started publishing these amazing color photographs. What we are seeing here for the first time ever in public is a man from the Earth standing on the moon. It's quite a remarkable thing to achieve in 1969. They even took a car and drove around. Typical Americans, you have to drive everywhere. And yeah, lots of sampling went on. So the Apollo missions, Apollo 11, 12, 14 to 17, took place between 69 and 72. Apollo 13 was aborted. Okay, Houston, we've had a problem here. That was an oxygen tank exploded, and Apollo 13 had to be aborted. Famous Hollywood movie starring Tom Hanks as Jim Lovell. It's worth watching. 382 kilograms of rock were brought back from the moon. Got a lot of stuff to look at, basically. 12 astronauts walked on the moon. Let's have a look at where they landed. So here's our orthographic projection of the moon. This is the near side. This is the landing sites of the Apollo missions. What we have here is Apollo 11, 12, 14, 15, 16, 17. Now, it's not a coincidence that Apollo 11, Apollo 12, and Apollo 14 all landed in relatively flat terrain. This was so the engineers could get a much better idea from the earlier Apollo missions as to how to deal with the terrain on the moon. Okay, they wanted somewhere billiard ball flat that you could land the lander on, whereas the geologists actually wanted to go and look at nice rocky outcrops. So it's not until the later Apollo missions that they attempted to put the missions down on the lunar highlands. Lunar samples, mostly breccias held together by impact melt. So the moon has been impacted throughout the whole of its history, and those impacts are strong enough to actually melt the lunar soil. And it melts the soil and binds fragments of ejecta together into a breccia. We have lunar regolith and regolith breccia. That's the sort of soily and rocky stuff that's littered on the surface. The regolith breccia is very useful because it's formed by impacts. So you actually end up with a natural laboratory sampling material from quite a long way. So they were quite well collected. Pristine highland rocks, uncontaminated by mixing, and lots of lavas. This is lunar regolith sampling using the brake. Okay, it's a proper NASA rake. It's not from B&Q or something like that. The idea was you drag this along, take fragments out of the regolith, and as I say, those fragments are from the result of impacts, so they actually are a wide range of lithologies, and that gives us a good idea of the general lithological variability on the moon. Most recently, the Chang'e 4 Chinese expedition in 2020, which was an autonomous expedition, unmanned, they put a ground penetrating or lunar penetrating radar down and have determined that the lunar regolith is in fact stratified to at least 50 meters in depth. So there's a stratigraphy of this collision activity. That's a lunar breccia. So you can see the fragments of rock. The dark black colored material is glass, and that's glass which is formed by the melting of the lunar dusty soil. All right, this is a very important rock. The engineers called it 15415, 15 standing for Apollo 15, 415 standing for sample number 415. It was spotted because it was sitting on its own, and the sunlight caught this rock and reflected off it. And one of the astronauts went, oh, I'll have a bit of that, went and got it. It's Apollo 15, came from there, and it's been renamed the Genesis rock, a very famous sample. What does the Genesis rock look like? Well, it looks like this in thin section, pretty dull, colorless. Let's put the polarizers in. Plagioclase feldspar. Like it's all plagioclase feldspar. There's some high relief bits and pieces, top left, middle center, top right. They're pyroxenes. Bottom line is entirely made of plagioclase feldspar. So what's significant about that? And the feldspar is calcium rich, exclusively calcium feldspar, no sodium in it. What was important about it is that we have plenty of geochronology on these anorthosites. They lend themselves very well to geochronology using the samarium neodymium technique. So I've got some here that were published in 94, 2003, and most recently in 2020. So these moon samples are still giving up their secrets, 4.3 to 4.6 billion years old. Hence the Genesis rock, because it is likely that these are the first rocks that formed on the moon. These must have formed very early in lunar history. The accepted age of accretion of the solar system and the first formation of the silicate planets is now 4.567 billion years. That was published 2 years ago. So we can see that these anorthosites were being formed very, very early in lunar history. And on the right there is a whole set of ages. Some of them are called fans, that's ferroanorthosites. The other ones are some similar rocks, but some of them contain some olivine, so they're actually troctolites. But they're really, really very, very old rocks. This is the age of the Lunar Mare, considerably younger, 3.1 to 3.9 billion years. Divided here into a high and low titanium group. Okay, there's some debate over whether the age difference is real or whatever. Talk about that a little bit later on. But the Lunar Mare postdate the anorthosite highlands crust quite significantly. Now, here's a clever instrument. Kagoya was a Japanese mission, and they had an instrument called Selene. All these things, by the way, are acronyms, and I have no idea what Selene actually stands for. I'm not even going to attempt to try and remember. This is imaging how much plagioclase feldspar is on the surface of the moon. Okay? The resolution below 50%, or at 50% or lower, is very poor indeed. But what you see there as bright colours is more than 75% plagioclase feldspar. This is an entire area of the lunar crust made just of feldspar. The black area is the lunar maria, which are made of basalt. Let's go and look at the other side of the moon. Well, there we go. There's an awful lot of plagioclase feldspar on the other side of the moon. Down at the bottom there, the blue area, is a large impact crater called the South Polar Aitken Basin, and that's why it appears blue. It's an area of where the plagioclase has been disturbed by impacts. So a large proportion of the moon is made of this very, very ancient material. So we divide the moon into these terrains: the Procellarum creep terrain, the feldspatic highlands terrain, there's the lunar mare, and additionally we have this big thing called the South Polar Aitken Basin, and that's how they're distributed around the moon. Okay. Stratigraphy. We can actually erect quite a good stratigraphy of the moon. We can calibrate it on isotopic ages from return samples. But the other key thing is the length of time that a rock's been exposed to the surface is related to its impact history. So things that have been exposed for a long time have undergone lots of impacts. And there's a method called crater size frequency distribution measurements, which are very robust and give us accurate ages for unsampled parts of the moon. And this is how it works. Along the bottom is an age. On the side is cumulative frequency of craters per square kilometre. And the moon stratigraphy is divided into pre-Nectarian, Nectarian, Imbrian, Eratosthenian, and Copernican. So where are we at the moment? Well, there's the Phanerozoic Precambrian on Earth, okay? And those things, the anorthosites, are all pre-Nectarian. So they plot right over there. Then there was an astronomical period called the Late Heavy Bombardment. And as the name suggests, this was a period of huge amounts of meteor impacts onto the moon. And the Late Heavy Bombardment took place between about 3.8 and 4.1 billion years ago. Then, after the Late Heavy Bombardments, we had the Lunar Maria. There they are, between about 3.1 and 3.8 billion years. Okay? There is a hint from cratering that there might be some younger lavas. And the Chang'e 5 mission that the Chinese, again, an autonomous lander in 2022, they found some glass beads on the surface of the moon, tiny little glass beads, which they dated. And it's entirely possible that there might be some very young volcanic activity on the moon, although that's subject of a huge amount of debate at the moment. All this is happening in very, very deep time. The USGS have come up with this. This is the unified geological map of the moon, and each of the color units on it are colored by age. So the red is the Maria period, okay? And you can see that the yellow and blue cratering events are post-Mare, and so on and so forth. All the cream-colored stuff is anorthosite, 4.5 billion year old anorthosite. Near side of the moon, far side of the moon. Far side of the moon, devoid of Mare, lots and lots of the cream-colored anorthositic crust of great antiquity. This is a fabulous thing. It was only published about 5 years ago, and it's, as usual with USGS, you can download a massive PDF of this for absolutely free. It's fabulous. Just an interesting point, which will become relevant later on. There's some parts of the moon, like the Imbrian Basin, and this is actually an impact crater that's been flooded later on by Maria basalts. And this thing, the Apennine front, there we are, it's on a geological map. The Apennine front is made of these ancient anorthosites, and that's actually flank uplift from a major impact event. And the other interesting thing about this area is just off the bottom of this slide is where Apollo 14 landed, a place called Fra Mauro. And that area is completely littered with breccias made from this Imbrium collisional event. This is significant for one very simple reason, is that there's the Mare outlines on the near side of the rune. Using gravity anomalies, we can map the thickness of the lunar crust. And what you find is the Imbrium basin has some of the thinnest crust on the moon, less than 10 kilometers. Okay? So the lunar maria are occupying areas, many of which are impact craters before Mare volcanism, and they have thin crust. If we go to the far side of the moon, we find we've got very, very thick, just anorthosite crust. So again, we have this wonderful thing called the lunar dichotomy. Let's put this into perspective. This is the age of the oldest object known on Earth. This was published in 2001. 4.4 billion-year-old zircons. Okay? Interesting thing is, these are zircon crystals in a granophyre, which is in a conglomerate, which has been folded and metamorphosed and intruded by a granite that's 2.9 billion years old. So we've got a good history here, but it's restricted to tiny zircon grains. Let's put that in perspective. They're there, so very, very close to the age of lunar anorthosite. Big difference, of course, is we've got a lot of lunar anorthosite. We have about a dozen zircons. This is a characteristic feature that the Earth has been resurfaced many, many times by plate tectonics. And this resurfacing event on active planets is what destroys the old geological record. That's what makes the moon so interesting and fascinating, is it's fossilized at 3.9 billion years. All right, oldest rocks in Scotland, well, 3.13 billion years. Where do they fit? They fit there. So the oldest rocks in Scotland are younger than the lunar mare. So the moon has stopped its volcanism before the oldest rock in Scotland ever formed. Look at it in terms of the geological timescale. There's the moon timescale. Pharaonian and anorthosite crust there, late heavy bombardment, mare volcanism, oldest zircons on Earth, oldest rocks in Scotland. Not much happening. Really not much happening in the moon from 3 billion years to the present day. What do we know about the internal structure of the moon? Very little. Problem is, we don't have plate tectonics, so we don't have lots of earthquake activity. Seismometers were deployed during the Apollo missions, and technology at the time was such that the batteries went flat. So one of the big things about future missions is to put more seismometers. So we have very, very limited moonquake evidence to work on, except there might be a discontinuity some way about halfway down the depth of the moon. Right, lunar magma ocean. Why have we got a crust made of feldspar? The explanation is actually quite simple. If we look at a density depth diagram, then liquid magma is always going to be less dense than most of the minerals that crystallize from it. Now, we can get estimates of the density of the lunar magma ocean. There are various ways of bulk chemically estimating this. It's not too difficult. And you find something very simple, that plagioclase feldspar anorthite is less dense than the lunar magma ocean. But all the other minerals that crystallize from the lunar magma ocean are more dense. So the general idea is that we have a convecting magma ocean. The first minerals to form with decreasing temperature are olivines and pyroxenes, and they sink. So we end up with olivine pyroxene cumulates. When plagioclase joins the crystallizing assemblage, it's more buoyant, it's less dense than the surrounding magma ocean, so it floats. So the anorthosite crust of the moon, probably, is the scum floating on the top of the lunar magma ocean. And when you take this a little bit farther, as the lunar magma ocean starts to near complete crystallization, you end up with a little zone at the top of residual liquid. This residual liquid is very enriched in all the strange trace elements that don't normally enter the phases that have crystallized earlier on. And that is probably our creep layer. That's where all our potassium, phosphorus, and rare earths are. So the generation of the north-like crust is probably flotation due to crystallization of the lunar maria, lunar magma ocean. This type of process is likely to be very, very similar on the other terrestrial planets. Right, the problem we've got is then with basalts. Of course, we can have the lunar magma crystallizing. That's how we form the ancient Northern crust. But where on earth did the lunar mare basalts come from? Okay, well, what are they? We've got olivine basalts, pigeonite basalts. Pigeonite is a calcium-poor pyroxene. It's very characteristic of lunar samples to have calcium-poor pyroxene. On Earth, we don't. We get augite, which is calcium-rich. Ilmenite basalts, we don't see these at all on Earth. And creep basalts. Okay, there's also some lunar minerals. Aramalcolite, that's Armstrong, Aldrin, and Collins, the 3 astronauts on Apollo 11. Tranquilityite, that's fairly obvious where that comes from, and a thing called pyroxferroite, which is a bizarre iron 2+ calcium silicate, although we do know that exists in some terrestrial samples. Right, I'm going to show you some thin sections of some of these rocks now. Okay, so I have to jump out of PowerPoint and do this without successfully switching zoom down, because they're rather good. This is the UK virtual microscope, and the UK virtual microscope is home to all the thin sections ever produced for the Apollo missions. Okay, and this here we have a magnesium-rich basalt. It's pretty boring there, you see. It's brown. We look at the microscope like that. Okay, in plain polarized light, I think you can see 2 basic colors, a sort of a brownish color and a colorless color. Colorless color? Can't have that. If we put it in cross polars, we find that these things, which are colorless, are olivine, and these things with the purplish hue are pigeonite. Now, there's something weird about these olivines. If I gave these olivines, this thin section, to any of my undergraduate students at first year and said, can you find the olivine? They'd say no, because none of the olivine has the characteristic curved cracks, alteration, black alteration in it. Why? Because there's no water on the moon. So most of the alteration we get in basalts like Arthur's Seat and so on, the olivines are practically all disintegrated. They're disintegrated by hydrothermal activity. Here we have a 3.9 billion year old rock, which is as fresh as the day it erupted. Now, the UK virtual microscope is great because it has these little things in here, and we can go into that, and we can rotate it around and demonstrate that that is pigeonite with small inclusions of olivine in it. Okay, so what else have we got? That's an olivine basalt. Let's have a look at a little bit of ilmenite basalt, which is my favorite. I think this is my favorite here. Ilmenite basalts, really, really unusual samples. Don't see anything like this on Earth. The black things, FeTiO3, are ilmenite. They are phenocrysts. This is a magma crystallizing phenocryst of ilmenite, and it consists of ilmenite, which is the opaque stuff, calcium-poor pigeonite, and some bits of residual feldspar in the ground mass. And that's fairly typical of these ilmenite basalts. Again, we can have a look across polars, and you can see there, again, pigeonite with some olivine in it as well. We then have pigeonite basalts proper. Okay, and here's a nice example. These long needle-like things are pigeonite, which is, again, it's a calcium-poor pyroxene. This particular thin section has a bit of history, because in 1972, this thin section found its way to Aberdeen, and it was analyzed by electron microprobe in the days when Ian Parsons was on the staff there. So this has a direct Scottish connection. And that's a pigeonite basalt. Now, the way it works is that olivine basalts are the most primitive. with more fractional crystallization, you move on to pigeonite basalts. And then the ultimate crystallization is ilmenite basalts. So the ilmenite basalts are the more evolved. The other thing that we've got as well is creepy basalts. See if we can find you a creepy basalt. Let me just, that's the best one. Yeah. Creepy basalts aren't up to much. They're not the prettiest samples that you get from Lunar area. But what's strange about them is they have quite a lot of plagioclase feldspar in them. Okay. And these are these high rare earth, potassium and phosphorus rocks, also stuff full of thorium. So these are really, really interesting samples. And finally, so if you want to see some more theme sections, we can look at them later on. There is another odd thing that you find on the moon, and this is Apollo 17. There's a very famous YouTube video. If you go onto YouTube and search for orange soil, you'll find astronauts on Apollo 17 standing around going, "Hey, orange soil, we've got orange soil," and digging up shovel loads of orange soil. They were interested because the orange soil might have been soil that had been interacting with water. That was the thing. They get it back to the labs at NASA, and what do they find? They find that the orange soil is made of spheres of glass, basaltic glass. Again, glass, completely pristine, 3.9 billion years old. You can tell it's glass because if you put it in cross polars, it all disappears. Okay, because glass doesn't have a crystal structure. The really interesting thing about this as well is that the color of the beads correlates beautifully with their titanium content. So green ones, the titanium less than 2%, brown ones are about 8%, the black ones in there, 15% titanium. Now, one of the most important things about these is these are tiny little spherules. Advances in modern analytical techniques means that we can actually get ages out of individual glass spheres these days using laser technology. For sure, we can analyze rare earth elements and all sorts of things, practically the whole periodic table in a single glass bead. And this is something that the Chinese have been doing with their Chang'e missions. So there you go. That's what lunar basalts look like. I say plenty of time to have a look at some more of those towards the end. But let's do a little bit more theory. So we've looked at the different types of basalts. Yep. This is what they look like chemically. Just put this in if people like spotty diagrams. Point is, the gray splodge area on there of little dots, that's ocean ridge basalts from Earth. So if you look at the iron one in particular, you'll see that a lot of lunar basalts have twice the amount of iron content of anything that we see on Earth. And at the top there is these very, very high titanium basalts. Here's a weird thing. These are rare earth element profiles. Lunar mare, basalts, olivine basalts, pigeonites, ilmenite basalts, creep. They have rare earth patterns which are relatively flat, but they've all got a dip in them. And this dip is a dip at the element europium. Now, the rare earth elements are mostly, well, they're all trivalent, but europium has a little trick, and it can be divalent or trivalent. And on the moon in the reducing conditions, it's divalent. What that means is, if you've got any plagioclase feldspar anywhere in your system, plagioclase feldspar is a sponge for europium. So if you have a magma and you remove plagioclase feldspar from it, okay, and you look at the rare earth profile before it's removed and it's relatively flat, remove plagioclase feldspar, it'll be flat with the dip. Okay, so negative europium anomalies, as we describe them, are the result of plagioclase being removed from a system. Trouble is, the lunar olivine basalts, and the glass beads show this characteristic as well. The lunar olivine basalts have never crystallized any plagioclase. They've only crystallized olivine and pyroxenes. On Earth, we see rare earth patterns that look like this. This is a pickrite from Iceland. The grey one is an ancient 3.8 billion year old komatiite from Canada. This is a recent basalt from Hawaii. They're all planar patterns. There's no negative europium dip. We only ever see negative europium dips on Earth in really evolved rocks like rhyolites and dacites and things, not in basalts. But what we do see is things with positive europium anomalies that have accumulated plagioclase feldspar. So what's the relevance of this? The relevance of this is that if you look at the anorthosite crust, it's made largely of feldspar. It's got tons of europium in it, overrepresented compared to the other rare earths. All the lunar mare and the glass beads and so on, volcanic rocks, which are later, negative europium anomaly. Could the two be connected? This is an important point. So let's have a look. So let's say the lunar magma ocean starts to crystallize. First of all, first thing to crystallize out of it is olivine. Then it crystallizes orthoperoxene and olivine together. Then we get some plagioclase, augite and pigeonite, and then we get plagioclase and ilmenite. How do we know? We know because we can do laboratory experiments to simulate how these magmas would progress in terms of fractional crystallization. And that's what's being done. The rare earth pattern of that would be that shape. That would be that shape. It's moved higher up because the rare earth elements don't like olivine, so they stay in the liquid, so they become more enriched. And when we get to there, we start producing plagioclase. Plagioclase floats. So that means that this residue here now has a dearth in europium because it's gone into making that positive anomaly. And the more we continue that process, the more we get negative europium anomalies. Now, here's the thing. The theory is that to generate the mare basalts, what you're actually doing is you're melting the crystallized lunar magma ocean. You're remelting it, okay? So plagioclase flotation gives you the positive europium anomaly in the anorthosites. That causes negative europium anomaly in your crystallized lunar magma ocean. Deepest cumulates are unaffected. And this is all taking place in about that depth on the moon. So one of the most important things is maybe we're remelting the crystallized lunar magma ocean cumulates to generate the mare basalts. If we are, how does it work? Why would they suddenly start melting a few 100 million years after the formation of the moon? Okay. As I say, melting experiments, we know pressures and depths of melting. There's a pressure-depth relationship here, which is very different from that on Earth. And this comes down to gravity. So to achieve 1 gigapascal on Earth, it's 32 kilometers. On the moon, to achieve 1 gigapascal, it's 200 kilometers. It's because the gravity is not acting to produce the high pressures. So we've got good simulations of where these basalts come from, and they're coming from a region somewhere like that. Let's have a look at densities again. Densities become important. Olivine, when it crystallizes, the olivine that crystallizes at the highest temperature is magnesium rich. And as we go down temperature, olivine becomes more iron rich and gets denser. So we can put on there a line showing the density of the olivine in the lower part of the cumulates. You can then do this calculation for the whole column of lunar magma ocean. And what you find is this. You get a line, and you find that the lunar magma ocean cumulates are density graded upwards. This step here is a hike in density because of the first appearance of ilmenite, which is very dense off the scale here. And the one at the top is other late stage spinels. So what we've now got is a pile of crystals, probably a crystal mush rather than anything else. There might be some liquid left in it, with the heaviest ones at the bottom, the lightest ones at with the heaviest ones at the top, lightest ones at the bottom. So the idea is that that happens, and the whole thing turns over to generate some kind of equilibrium in terms of its densities. That's fine, you can do that. I've got it very well organized, of course, there. It's not going to be like that. It's going to be all streaky and horrible and blebby, okay? But key thing is, right at the top there, the creep layer, the residual liquid, is actually firmly attached to the crystallized anorthosite. And of course, the crystallized anorthosite doesn't get involved in the overturn. So we maintain that creep layer right at the top. It's a bit like the lithosphere, a bit like the mantle lithosphere that we find beneath continental crust. The other important thing is, if we look at the temperature profile before overturn, of course, it's hotter, deeper in the moon. Turn the whole thing over, you invert the temperature gradient. So now what we're doing is taking hotter material from depth and moving it to shallow levels. And when you take something hot and decompress it, its reaction is to melt. That's how melting works on Earth. It's decompression that causes the melting, not elevated temperatures. So we think what's going on is that between those two solidi there, just melting is possible in that region. So the current theory is that this lunar magma ocean was almost entirely crystallized. It was density unstable. It flipped itself over, started therefore to melt, and we generated lunar mare basalts. And this on the left here, it's a paper by Elkins, Tanton et al. From 2015. And it's just simply showing very specifically for some different basalts from Apollo 15, how they relate. So the idea is we can have different sources at different depths, and it's a kind of quite heterogeneous system. Why then did it take so much time between the formation of the lunar magma ocean and the North Site crust, and then it's later on that mare magmatism starts? This is all wrapped up in the lunar dichotomy. And to be absolutely honest, there isn't an answer. This is something that's still heavily debated. One argument is that lunar dichotomy owes itself to a differential impact history on the near side of the moon during early history. So I mentioned the Imbrian Basin being thin crust and the other mare areas being thin crust. It's entirely possible that preferential bombardments thin the crust on the near side, not the far side. So when the lunar magma ocean became unstable, it was the shallowest, thinnest crustal areas where magmatism started, and that gives you the lunar mare. Okay. Other one is an early Earth influence, which is called partly the tidal interaction theory. One of the things about planets in eccentric orbits is as they approach another body which has a large gravitational field, they get squished, and as they move away from it, they get unsquished. They actually structurally deform. And there are lots of calculations done. One of Jupiter's moons, called Io, is the most volcanically active moon in the solar system, and it is driven entirely by what's known as tidal heating, which is a continually squishing and unsquishing of that body. So it's entirely possible that the eccentric orbit of the moon around Earth has caused variable tidal heating, and specifically because it's tidally locked, it happens on the near side, which is closest to Earth's gravitational field. Internal heat differences, who knows? Yeah, wave your arms, that's fine. Okay. All right, so nearly there. What are we up to at the moment in Aberdeen? A few things. Most of what we can do with lunar rocks, you can't get samples. You have to be a 9th generation American Trump supporter to get access to samples from NASA. So you have to deal with something else, and that's GIS data. First thing you need is a student who understands GIS data. So I use MSc students for this purpose. GIS from the moon, we're talking hundreds of gigabytes up to terabytes of data to actually process. So it's not something for the faint-hearted. And what we've been doing is, I showed you maps there of titanium and iron abundance. Well, as a petrologist, I wouldn't be particularly interested necessarily in how much absolute titanium and how much iron was in a rock. I'd be more interested in how their ratios vary through time, because the ratios are more likely to reflect source differences. I think we do commonly as petrologists. So what we've done is we've modeled fractional crystallization from data from lunar return samples and established a relationship between iron-titanium ratio RA types, and then remapped the lunar surface on the basis of iron-titanium ratios. Okay. This is just to show how clever we are. This is a crystallization model, thing called Petrolog3. We plug known starting compositions in, and we tell it what pressure we're interested in, and it goes away and calculates at what stage during crystallization different minerals come on the liquidus. So up here, for example, we've got a high titanium starting sample. It first of all crystallizes olivine plus liquid. At that point there, it'll start to crystallize ilmenite. And as it crystallizes ilmenite, the residual magma, of course, decreases in its titanium content because we're taking the titanium out and putting it in the ilmenite. So we do that, and we do that for iron and titanium, and then we take the ratios. And what's interesting is you can divide an iron-titanium ratio diagram into ilmenite basalts down here, pigeonite basalts here, olivine basalts further up, based also on which lunar mission you're in. But the striking thing is that the ilmenite basalts, all of them from all the Apollo missions, all plot way down here. So what we've done is looked at this lunar mare here, Fecunditas. That's the mare boundary. Okay, that's the titanium abundance, and this is the ratio of titanium and iron subdivided by color for the basalt type. So what we've been able to do over just the titanium abundance map is actually map out which are ilmenite basalts, which are intermediate basalts, and which are olivine basalts. That helps us in mapping actual lava flows at the surface. This is still a bit in its infancy. We've got several of these maps for the different mare, and it seems to work quite well. So that's what we're doing at the moment. Okay, what of the future? Well, 16th of November 2022, Artemis 1 was launched. This is the next of NASA's moon program. Okay. Artemis 1, there's a pathway for it right up to Artemis 3, it's supposed to be 2024. The continuation of the Artemis program and the continuation of NASA's input into space science is under total political control of the White House. And really, I don't want to go into any arguments about that, but there's a great deal of uncertainty. But one thing's for sure, the Chinese Space Agency and the Indian Space Agency are doing some amazing stuff at the moment. What is being done by India is fantastic because they have this massive legacy of mend and make do, and they have a fabulous ability to generate the most complex instruments out of stuff and miniaturize them. And I work with some of the Indian engineers, and what they can do in the laboratory is quite remarkable. So they've recently designed some instruments that are going to Mars, and these are going to measure the atmospheric conditions on Mars. I kid you not, they fit in a briefcase. They're fantastic things. Anyway, there we go. That's a potted history of the geology of the moon. And I hope you've enjoyed that. And if there are any questions and you want to see any more thin sections, please fire away.